This solution is looking at operation sequence analysis. The scenario is a college wishes to build a new campus with 6 different buildings, and the college wants to lay out the facility to reduce the amount of student or staff travel distance between these buildings. To give you some kind of context, you can see that the buildings, we've got lecture building, library, study hall, concert hall, aula maxima, and student services, but we're labeling those with just letters from A to F. So the whole point about this is trying to reduce the amount of pedestrian traffic between each of these different buildings. And the college has a fair amount of experience with this from its previous campuses. And what they've done is they've gone out with a survey board and they've just measured how many people are directly traveling between the different buildings. And all of that information is shown in this table here called the flow matrix. So we can see here specific quantities of people who are traveling between each of the different buildings from their previous campus. For example, the amount of people traveling between A and going straight to the building B is 8 people. And the amount of traffic going from building B directly to building A is 7 people. Let's take another example from the flow matrix. For instance, between buildings C and D, the amount of people who are traveling between those 2 buildings from C to D direction is 5. And I can see that here in the flow matrix. But traveling in the other direction, going from D to the building C, that is 15 people, and I can see this here in the flow matrix again. In this flow matrix, we've got a lot of useful information about the traffic between all of the different buildings, but we have the information going both ways. What we want to do now is we want to get an aggregate of all of those traffic so that we get a total amount of traffic between all of the different pairs of buildings. What we do in this case is we look at both directions between any one pair of buildings, and we add both directions' traffic together. For example, between buildings A and B, there's 8 people traveling, and between B and A, there's 7 people traveling. So the combined total of all of the traffic going between both of those buildings in both directions is 8 plus 7, and that equals 15. And every time that I add these different numbers together, I'm going to bring them over onto the top right-hand side of the matrix. And this is what gives me this triangularized feel. And now it's a case of moving through each of those different pairs and doing the same process over and over again. Take one more example. We'll look at C. The traffic going between C and A is 20. The traffic going between A and C is 10. So therefore, 10 and 20 is 30. So the aggregate traffic going between buildings A and building C in both directions is 30. At this stage, you're probably recognizing a pattern. Between each of these different pairs, every cell that I select on the top right-hand corner of this flow matrix, its corresponding number that we need to add together to get this aggregate pair is just whatever is opposite across this diagonal line of different hyphens. So 7 and 1, 8 and 0, 6 and 0. I'm just picking out all of the different pairs, the corresponding matching pair across that diagonal, and if you look at it, it will always match up between the different pairs. Take one more example and just point that out. 8 and 0. So 8 is the traffic between F and C, 0 is the traffic between C and F. With that knowledge, it can become quite quick to add together these pairs. Every pair that I add together, I'll just put in the corresponding number, and the number will disappear from the bottom left-hand side, and it will appear as the aggregate number on the top right-hand side. And there we have our triangularized flow matrix, or our aggregate flow matrix. Again, the whole point of this exercise is to try and reduce the amount of pedestrian traffic between these different buildings. Now that I've got my aggregate flows between each of the different pairs of buildings, I want to create some type of metric that will allow me to compare different layouts of the different buildings and the resulting amount of pedestrian traffic that is caused by those layouts. Let's take an initial layout. And just in this example, the initial layout, just because we've labeled the buildings A, B, C, D, E, and F, I'm going to lay them out in that alphabetical way, but really there's no higher meaning in that layout. I just have to have some starting point, and that's the starting point that I'm choosing here. When I look at this layout, there are certain pairs of buildings that are right beside one another, so they're adjacent to one another. For instance, between A and B, those buildings are very close together, they're adjacent, they can't be put any closer together on the map of this new campus. When I'm comparing different layouts to one another, the fact that buildings A and B together, that they are right beside each other, the pedestrian traffic between those buildings don't have very far to walk. Compare that with the traffic between buildings A and C. The traffic between A and C has a lot further to walk because those buildings are not adjacent. A and C are a non-adjacent pair. With that reasoning, when I'm trying to compare different layouts of buildings, I'm only going to focus on non-adjacent pairs. The buildings that are paired together and they're beside one another, or that they are adjacent, the traffic between them is negligible, or the distance traveled is negligible, so I'm going to ignore those. So just focusing on the non-adjacent pairs, we have got the pair between A and C, the pair between A and F, the pair D and C, and the pair D and F. If you look at any other pair in that layout that we're looking at the moment, all of the other pairs are adjacent to one another. Looking back at the non-adjacent pairs, if we look at the distance between each of those different pairs, so for instance between A and C, the distance based on this grid that I have in behind my set of buildings, I see that the distance between A and C is 2, so that's 1 square to 2 squares. The distance between A and F is also 2, 1, 2. The distance between D and C is 2, 1, 2. And the distance between D and F is 2, 1, 2. Now that I've identified all of the non-adjacent pairs, let me list them. And what I want to do now is I want to get a particular load based on the product between the amount of traffic that's going between the two different parts of each pair, and also the distance that the people are traveling. For instance, A and C. The amount of traffic between A and C is 30, and I can see that from my triangularized flow matrix. So that's 30 multiplied by the distance, which as we previously identified is 2. So the product of each of those is 60. And I do that for each of the different pairs. And we can see the traffic between A and F from my triangularized flow matrix is 6. The distance is 2. Product is 12. The traffic between D and C is 20. Distance is 2. The product of those is 40. And the traffic between D and F is 6. By 2 is 12. And I want to get the sum of all of those different loads, and that sum is 124. That 124, it's not that I can apply any particular units to it. It is just a weighting. It's a metric that I can use to compare different layouts to one another. And if we think about the overall goal of this exercise, it is to reduce the amount of traffic that people have to travel between all of these different buildings. We want to lay out the buildings in such a way that we bring that non-adjacent load, that non-adjacent weighting, as low as possible. And if we think about it, that makes sense. All of these numbers here, 36, 26, that is the amount of people that are traveling. And all of the twos are the distance that they're traveling. And we're adding all of those different weightings together to get an overall weighting of the layout. That is the amount of distance that is traveled by a number of people. The next step is to think about how can we rearrange the different buildings so that we can bring this non-adjacent weighting lower. And if we think in a strategic way about this, we've got A and C. I can see the number there is 30. That results in a weighting of 60, which is a big component of this 124. So if I'm looking to rearrange the different buildings there, the fact that A and C are non-adjacent, that's causing the weighting to be quite high. If I can reconfigure the buildings so that A and C are close together, so that they're only one apart and therefore are considered negligible and ignored, then that will bring the non-adjacent weighting lower. So if our first step is to try and move C and A closer together, what about I could possibly take the C building and move it up to this area here, up above A. Well, let's trial out that layout by moving the building C up to this area here. Considering this layout, we have to pick out what our non-adjacent pairs are. And again, these are the pairs that are more than one apart. So I can see that C and D are a non-adjacent pair. C and F are a non-adjacent pair. D and F are a non-adjacent pair. A and F are a non-adjacent pair. And lastly, C and E are also a non-adjacent pair. So compared to the last layout, we actually have 5 different non-adjacent pairs in this layout. Again, let's pick out the distances that people are traveling between these non-adjacent pairs. So between C and D is 20. Between C and F is 8. Between D and F is 6. Between A and F is 6. And between C and E is 8. With reference to the grids behind the actual buildings, I can see that each one of those non-adjacent pairs are again 2 apart. So C is 1, 2 apart. C and D is 1, 2 apart. C and E is 1, 2 apart. D and F are 2 apart. A and F is 2 apart. So each of those different amounts of traffic, they're going to be all multiplied by 2. And the results of those products are 40, 16, 12, 12, and 16. And that results in a total of 96. And that's an improvement. It's a lower weighting compared to our initial layout, which was a weighting of 124. At the end of this layout, again, we want to look and see if there's any improvements that can be made. So looking at the weighting for C and D resulting in 40, that 20 there of the amount of people aggregately going between C and D of T, it's quite a large amount. That would be the next thing that I would be looking to reduce. And the way to reduce it again is to move C and D closer together, to make them adjacent rather than non-adjacent. And so we'll move on to a third layout. Trying to get C and D closer together, I will swap C and A. And picking out the non-adjacent pairs of this layout, while I see A and E, C and F, A and F, A and D, and D and F. and we pick out the movement of people between those pairs. So between A and E we have 15. Between C and F we have 8. Between A and F we have 6. Between A and D we have 0. We have D and F, we have 6. Each one of those pairs again is a distance of 2 apart, so multiply them. And the result of that is 15 by 2 is 30. Next one is 16. Next one is 12. Next one is 0. And the next one is 12. And that results in a weighting for this layout of 70. At this stage, it's probably becoming clear to you, when we're looking at this triangularized flow matrix and picking out what are the different combinations that I would like to see and what are the different combinations that I'd like to avoid. Well, obviously, any time that we see a 0 or very low numbers, we would like to actually bring those into the equation above or instead of any of the large numbers. And that's essentially what we're doing at the moment. If you look back, we had this 40 involved for a stage. We also had a 30 involved. We're getting rid of those high numbers. We're bringing in these lower numbers here, 0, 8, 6, 6. And obviously that will result in a lower weighting. Even though it sounds simple, the difficulty is when we're trying to assess what rearrangements to do in every subsequent stage of the layouts. When we move a particular pair so that they're adjacent and taking out one of the large numbers, it has a knock-on effect that it could actually bring in lots of other numbers from the triangularized flow matrix as well. These hopefully might be low, but it's trying to keep an eye whether they're low numbers that it's bringing in or high numbers, and trying to weigh up all of the different options. That's what makes this problem quite difficult and quite challenging. The other aspect of some of these different layouts that we're seeing so far, we can see that this layout 3 and also the layout that we had in stage 2, they involved 5 different non-adjacent pairs. And that, of course, has the effect of bringing in more numbers into the equation, which often encourages a higher number. So that's also something to keep in mind, is generally we'd like to have the lowest number of non-adjacent pairs. With that in mind, I'm looking at this F that is out here on its side, and I'm toying around with the idea of moving that F up to this area here so that it's adjacent to A. That will result in a lower number of non-adjacent pairs. It will result in just 4 non-adjacent pairs then. That could play to my advantage and could result in a lower weighting. But just as I said before, every time that we move a building from one place to another in a layout, we have to keep in mind not only will we gain some, but we might also introduce other numbers into the equation. And so from this instance, looking from moving F to this area here, that would mean that F and E then become a non-adjacent pair. And I should kind of weigh up from my triangularized flow matrix what number would be introduced in that case. And here I see it here, it's F and E is a 10. So it's introducing a 10 in that case. If I try and think ahead as far as possible, and when I move F into this area here, I introduce F and E, which is a 10. Possibly if I exchange E and B, so move B down to this area and E up to this area here, that would mean that instead of F and E being non-adjacent pairs, F and B would then be a non-adjacent pair. And that would take out a 10 and put back in an 8, which would reduce my weighting. On to layout 4 then. As we suggested, moving F into this area here and swapping B and E. This layout results in the non-adjacent pairs of A and B, A and D, F and B, and F and D. All other pairs are adjacent. And so, summing up the traffic between each of those pairs, taking these numbers from my triangularized flow matrix, so I've got A and B is 15, A and D is 0, F and B is 8, F and D is 6. All of those non-adjacent pairs are 2 apart, so multiply them all by 2. Get the results. They are 30, 0, 16, and 12. And get the sum. It gives us a total of 58. Again, 58 is an improvement on all previous layouts, so that's a positive thing. The difficulty is when we go through a lot of the different layouts, we're getting lower and lower numbers. It's becoming harder and harder to pick out improvements. And the difficulty is knowing when you're finished. And what we're trying to do here is make sure that any of the big numbers that are here in any of the traffic identities that we have between the different pairs, that we have gotten rid of all of those big numbers that we can, and we've introduced as many low numbers as we can. So obviously we'd have a lot of bias towards any zeros, any 2s or 3s, things like that. Looking at this example here, we still have a 15, which looks a little bit large, and I would be anxious to try and get rid of that. But just weighing up all of the different options, if I move B and C, just swap those around, fair enough, I'll be getting rid of the 15 between A and B, but I'll be introducing the number that has traffic between A and C. And I can see here from my flow matrices that that's 30. So that's going to actually increase the weighting. If I try and move A closer to B, let's say by swapping A and D, that means that I will get A close to B, will get rid of the 15 that I'm seeing here, but it will introduce a number between F and A, and that's 6, but it will also introduce D and B, and D and B is 40, and we definitely don't want to do that. And so at the end of the day, it's a puzzle that has to be solved. And you just have to play out all of the different scenarios in your head as best as you can. The alternative is that you go through every combination of all the different layouts of a set of buildings. But in this example, I've come to the conclusion that we've got the lowest weighting. So this is my optimum layout. And I can make a statement down the bottom of the example to that effect. Remember, in this example, the point of the exercise was to reduce the amount of travel that pedestrians had between different buildings in a new campus. But it's also worth noting that the same type of technique can be used when we want to increase or even maximize the amount of distance traveled for pedestrians between different parts of a campus or some kind of facility. A good example that I might give is just that of a supermarket where management might want to try and increase the amount of traveling time or the amount of time spent by customers within the actual shop. So therefore, if they take some kind of important items, such as the dairy counter, maybe the deli, maybe the fruit section, and they spread them out in a way based on my operation sequence analysis so that the actual non-adjacent weighting is increased or is maximized, then you're increasing or you're maximizing the amount of time that people are spending walking down the aisles. And therefore you're increasing the possibility that those customers will see different types of products on the shelves that they find attractive, and it may increase their impulse buying. And so the same technique is used as we've seen here, except instead of trying to find the lowest non-adjacent weighting, we try and reconfigure all of the different parts of the facility so that we're increasing or maximizing the weighting. And that's operation sequence analysis in the context of facility layout.